What does that mean? What are we saying as we keep going with this Reynolds number? That's that C sub D is constant. So what that means is that the C sub D of the model is going to equal the C sub D of the prototype. So what C sub D are we going to use for that? Based on this picture. The linear part, that's exactly right, where it is constant. All right, so you're going to use this C sub D. You're going to go back and use this equation, and that's going to give you the drag force. Does that make sense? Okay, so let's make sure, let's go back to that. I gave you the density and I gave you the viscosity. So all you need to do now is based on that, you have to find your C sub D. So they're equal, exactly, because the line is linear. This is what's meant as incomplete similarity. So you can only pick the points where it is linear, all right? So you don't need to do multiple points, because this is, as soon as it goes to this point right here, what you're saying is I'm going to extrapolate, and I'm going to assume that the C sub D stays constant after that point. And those numbers are all going to be the same. So you're going to find your C sub D. Yes, let me write that back out again because I didn't. Let's see. So yeah, your C sub D is, write this down, is equal to F sub D 1/2 rho V squared over A. Okay, so what C sub D is, it's called the drag coefficient, and it's actually a function of, as you might see, the Reynolds number. And it's a number that tells you, when we talk about liquid drag, that based on a certain geometry, configuration, whatever, this is going to be the coefficient of drag, all right? So, yeah, it is in chapter 9 because that's where we start talking about drag. And how you knew what it was equal to is, again, we started with, when we first did our first pi group ever in the class, we said that it was equal to this. And so if you look in the book, and you are going to have to look it up, what you find is that the actual, if we call this a pi group, right, we say that this is a constant. And if you notice, it's only a constant at a certain Reynolds number, and from that, we find that this is what the constant is, okay? So that's done by experiments that we haven't, that we aren't going to do. But that's what the equation for it is. And again, and you're going to see this, it all comes from these dimensionless parameters. Once you figure it out, then you plot one pi group against another, which is exactly what we did here. What I could have said is that drag force is a function of blah, 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 and velocity or whatever is a function of blah, 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 and then you would have found your pi groups. So there, now my cousin, geez, first it's my kid, now it's my husband, and estranged, in this particular case, it's not always achieved at higher Reynolds numbers, but you're right, because of your graph, that you're showing is only achieved. Ah, so is the C sub D of the model the same as the prototype? What do you think? In fact, let's go back. What we're really looking for is this drag force, which is equal to, and this is what you see it more like, 1/2 C sub D rho V squared over A. Okay, so where is that 1/16 going to come in? But we don't have an L here. This is what we're looking at. Exactly. So it's going to be in the area. So what does that mean it's going to be? If it's a 1/16 scale, what do we have to do with the area? Yeah, it's exactly right. We have to square. So when you get to here and you put in the area of what, because you have it, I think, let's see where you have the area, of the model, you're going to have to take that area and multiply it by 16 squared, okay? If it were a length, and you're absolutely right, then you just multiply it by 16 divided by 16. Usually if you're going to do a prototype, you multiply it by 16. Does that make sense? Good question. Again, y squared, this 1/16 is based on a length scale. All right? However, the area is length squared. Okay? And not that the L's are exactly the same, but what it means is if it's a 1/16 model, every single length scale in it, from the model to the prototype, has to be multiplied by 16. So here, because we have an area, it's 16 squared. If it were a volume, it would be 16 cubed. If it were a length, it would just be 16. And it doesn't matter whether it's actually a perfect cube or anything. Every part of that length are multiplied by 16. And I guess what we can go back to is if the model is 0.991 meters long, then the prototype is that times 16, or this times 16, or this times 16. Does that make sense? Good. Okay. Kind of hard to get back into this. So are we okay with this one? And if you notice in this particular assignment, there is a bunch of plotting, whatever. And the reason for that is because this is what you do with hybrids, and this is what you do with models. You compare data. And that's what makes them so powerful. Okay, so let's go back here. And what it says is plot the drag coefficient as a function of the Reynolds number. So we write the Reynolds number here. We write the drag coefficient here. And then we just plot the two. And you have enough information for both of them. Okay, so what L is used for the Reynolds number? It says the length scale from the Reynolds number is the truck width. Okay? Yeah. How big is it supposed to? I gave you the answer. I was so good. I gave all the answers when I posted it. Let's see if I have it here. No, I don't have it. So you can look it up online. I seem to think it's like 266, but I don't think so. That's it. Oh no, it's a little bit bigger than that. What'd you get? It's like 3,400 or something like that. All right, where would you, I think we said we were going to 4 next, if that's okay. Everybody's okay with this one? If I don't see any no's, then I'm going to assume yes. And in the interest of efficiency and my dinner, we're going to. Okay. So we have this axial flow pump. And by the way, that 0.8 meters cubed is, there we go, cubed. And I put it on the homework, but if not, it's 33.8. I thought I put it. I did check on it. 3,380. Well, what should it be? I'm not going to tell you. You tell me. I was just going to ask you for the units. All right. So we have a Q, we have an H, and note the units of it. An omega, we have a 2.5 kilowatt. That's the power, 1,500 RPM. That's the omega. Similar performance between the prototype and the model. We're looking for the H and the Q. That's where we're going to start with. And then we're going to figure it out. Okay, so the first thing it says is both the power and the head, or the head of the power, are functions of Q, omega, D, rho, and I also gave you the equation for the power. Okay? So what's the first thing you're going to have to do with this problem? Is this any better, Mo? Okay. What I need to do is actually talk into my computer as opposed to looking at my notes. So the first thing we're going to have to do is we're going to have to make pi terms. And we're going to have to make 2 sets of pi terms. We're going to have to make pi terms for H, and we're going to have to make pi terms for power. Okay? And so if you take a look at all of these, how many pi terms are we going to have for each one? Just sounds like I'm back. Yeah, right. You know what, I think it is 333. Let me do one thing because I think it might be the same. Is that any better? Okay. That's exactly what it was. All right. So everybody was saying, what page hasn't it? You know, I just said that for your own edification. You could go on Google, whatever. It's in chapter 8. I just wanted you to understand that it was a term that we use when we are talking about pumps. Okay. And I can find the page for you if you'd like. It's just that I wanted to make sure that people didn't ask me as if it, that itself were important, which actually it is. So yes, for both of these, you need 3 pi terms. So the good news is that they are very similar to each other. I mean, the bad news is that you have 3 of them. The other good news, and for this, note that I didn't say find the pi terms. You know what it is that you're looking for. So you know that your pi terms have to have Q in it, and you know that your pi terms have to have omega in it, and you know that your pi terms have to have diameter in it. If you are looking for your pi terms, yes. So if we look at the first one, remember it's the dependent variable, so it'd be H, Q, omega, D, rho, mu. So if you look at that, what you're going to see is if you start looking at the pi terms that you need, if you have all that information in 2 pi terms, don't bother finding the third. I mean, I wrote it out anyway, but if you have everything you need, don't do any more work unless I tell you. If it says specifically, find the dimensionless parameters, then you have to find them all. Here you don't, okay? So let's say, and it is true, that for both Q and what we have here, for both H and P, so that's actually, again, and this is one of the hardest things. How did I choose my repeating variables? So if we have, and what we can do, I'll start with H, Q, omega, D, rho, and mu, and I looked at, so this, 1 over T, L, M over L cubed, and M over LT. So what I chose, just looking at these, what would you choose? I mean, this is the simplest, and then this is the simplest, and then all you have to do is choose either one of those that has a mass in it. Does that make sense? I mean, you can choose any of them, but what you want to do is choose the ones that are the easiest. So you choose rho, and I've always chosen rho because mu I don't remember, but either of them would work. So we're going to end up with, and I'll actually, could you choose, excellent question. Could you choose Q? If you wanted to, absolutely. But once you do that, now you have an L cubed term over T. What are the units of power? Okay, so if it's, units of rho are M over L cubed. So what you looked it up, good for you. So it's M, let's see, L squared over T cubed. Exactly. So you must have gone back to chapter 1 to look that one up. Yep. All right. So we have our pi 1, and because you're going to have to do the work for this anyway, I'll show you what the 2 pi's are. One of them is equal to h omega squared d squared. Is this the first Monday of the month? Okay, I just wanted to make, yeah, that's exactly why. So they always test their sirens twice a day on the first Monday of the month. So don't run out. I'm at work. And I actually was here when the flood was here and we had to evacuate, but that's neither here nor there. We are not dying, that's good. So why are we only finding 2 of the pi terms? We could find all 3 of them, but if you can see in your first 2 pi terms, every variable that you need to solve the problem, and I haven't asked you to find them all, then don't bother. So they're not the same. But, all right, so for example, in this one, our pi 2 is equal to q. And again, you're going to have to figure this out anyway. So since you're here, I can help you out. But let's say, so if you look at what the question is asking, we already have h, we have omega, and we have q, and we have d. That's what we're looking for. So we don't have to keep going, but if I asked you to, then you'd have to find, I think it's this. And if you know, the reason is that mu, we don't need it in any of our calculations. And so then when we look at our power, we have something very similar. This is equal to P over rho omega cubed d to the 5th. And actually our pi 2 is exactly the same, and our pi 3 is okay, now am I back with you guys? Yeah. All right, so let's go back. That's going to be an arrow. What's going to be an arrow? Oh, this right here, yeah. I kind of got like that. When determining, why don't we say? That's actually a really good idea. I'll come back to the power. So Q is dependent on D, but you can't make Q into another equation using everything here. If, for example, you had velocity, then you could say, okay, Q equals velocity times D squared over 4, and they would no longer be the same. However, here, all you know, it's dependent on it, but you can't make an equation out of it. Does that make sense? Okay, so the first two terms have all variables. You don't need a third. Okay, I'll answer all these at once. The first, okay, let's start with the first two terms do not have all the variables. What they have are all the variables that we need. They do not have viscosity, but we don't need viscosity in this particular problem. Again, if I ask you to find it, then you're going to need to find all of them. Here, all you have to do is figure out a couple of things that I've asked you for. So you got what the second pi. So how did I get the two set of pi groups? I went through what we always do, which is find the three repeating variables. I just skipped that step because I figured you're going to have enough practice in problems 1 through 3. So I just skipped a step. Does that make sense? So if we had something in terms of what we actually have, yes. So would they L, W, and H? Oh, for volume. Yes, that's exactly right. No, you'd have two of them. I mean, volume you would just get rid of, or three of them. Yeah. So volume you just get rid of. Okay? And then later, if you wanted to find the volume, you already have the L and the W and the H. So let's see what I have here. Okay, I'm going to erase this because this doesn't have to do with that. All right, and let's see, I got a little distracted here. So, similar performance between the prototype and the model. What that means is that this right here, so this pi 1 that has to do with the head of the prototype has to equal the same pi of the head of the model. In addition, that has to be the same for the power. Is there a pi next to the, where are you talking about? We don't have a V. Oh yeah, I was just showing that Q was a function of those. Yes, there would be a pi. So you shouldn't get the same three pi terms for both H and P, and the reason is look at the units or the dimensions for H. That is not the same as the dimensions for power. You should get these the same, but these two are not the same. Yeah. Otherwise, wouldn't this problem be a lot easier? All right. So let's take a look at some of these. Okay. And what's the first one? And let's go back to the problem statement, right? We know that we have Q of the prototype and H of the prototype and omega of the prototype. We have, what's that, 2.5 kilowatts? What is that? Oh, so the head, again, physically speaking, it's how you judge the amount of power that you get or energy that you get out of a pump. Okay, so let's see, What did I ask? I'm sorry. So 2.5, so we have the power of the model and we have the omega of the model. So when we look at that and we look at our pi terms, which pi term looks like what we should start with? So we could start with that, our H, but we don't have, we have the head of the prototype, and remember what we're looking for, right? But what else do we have? So if we look at Q, which has our Q and our omega, and that is what I would use, what we can say is that the Q of the model divided by the Q of the prototype is equal to the omega of the model times the omega of the prototype, and then this cubed. All right, so that starts to help us because we have both of the omegas and we have that prototype, all right? The Q of the prototype. But somehow we have to figure out, I'm looking at my notes, sorry, I know this is a little, no. We need to figure out the ratio. So where are we going to figure out the ratio? What information do we have to help us figure that out? And again, let's go back to our pi groups. So again, so if we look at these pi groups, right, you say, now pi 3 is not going to help us because we're just going to get a relationship. The mu's are going to cancel out and the densities are going to cancel out. So can we use the equation we have for power? So if we use the equation we have for power, now you're getting there, right? The power pi groups, what can we calculate? We can calculate the prototype power. So what we can find is this is equal to rho times Q times these. And we're given all of those. So now that we know that, now as somebody said, we're going to go back to the power pi group. So the power pi group, right, says that the power of the model over the power of the prototype is equal to the omega of the model divided by the omega of the prototype cubed, the diameter of the model divided by the diameter of the prototype to the fifth, and this ratio. And so let me go back to where we got that. We got that from this pi group here. Okay, what we said is okay, because they're similar, this pi group for the model equals the pi group for the prototype. And so if you look here, what is this? First of all, what can we cancel out? Right. So they're both in the same fluid, so we can get rid of this. You could do either one. You could solve. I solved in terms of ratios, but the problem is we don't have enough information. Like, for example, here, which is what you're talking about here, what can we solve for in this particular problem? we can only solve for the ratio. So what you have to be careful of, don't skip ahead and say, okay, we know that the diameter of the prototype is 0.25. We don't know that yet. So what we have to do here is we're going to solve for this ratio, because we have this, we calculated this, and we have this. So once we solve for that ratio, what can we then do? What can we then solve for? Now we can find the Q, right? Because all we needed was that ratio. And take a look, what else can we solve for if we're looking at our pi groups? Exactly. When we look at our pi 1, right, we have, again, I'm hopefully people aren't getting too seasick. We have our h sub p, we have our omegas, now we have the ratio of our diameters, and now we can solve for that. So we haven't solved for anything, any like diameters yet. What we've done, how to get the, okay. So if you take a look, and we'll go back to our pi. So our pi, I think this is 1, is equal to, and our power divided by our rho, omega cubed d to the 5th. And because they're similar, what that means is this is equal, and the m is the model, and now this is the prototype. And so now what we did was rewrite it, sorry, this is prototype, in this. And that's how we were able to solve for the ratio. Does that make sense? And so pump head, again, is what the power it takes to run a pump at a certain pressure or flow rate. Okay? So we do the same thing. We can find our Q there. And then because we have, so we know, we don't know any of the diameters, but we know this ratio. And so once we know this ratio, then when we know what we're given here, which is the diameter of the prototype, now we can solve for this. And that's what you're going to see in these problems. Sometimes you have to put together a whole bunch of things and just figure out ratios. So how did we get Q equals W times D? If you see in the power in this, it's this. I gave you the equation. I'm not sure where you got power equals W times D. Oh, you mean this? We got this, and now you should probably understand it. We got that from this pi group here. Are you okay with that now? Okay. So is it from the second pi group? So we'll go back. Remember, we have two separate variables. So it is the first pi group of the second variable, power. So we had 2 pi 1s, 2 pi 2s, and 2 pi 3s. So does this make enough sense that we can go on to a second question, or? By the way, in my opinion, I thought this was the toughest problem. So if you understand that, then you're in really good shape. All right, where should we go next? Besides to the candy drawer. 7 and 3. So we'll start with 3, and then we'll go, because 3 I think should be pretty quick now because we understand more, and then we'll go to 7. All right. So the first thing that it asks, now do 7. Let me just go through 3 first, and then I absolutely promise you we will go through, because this will be very easy, all right? Because remember, what is the drag coefficient? We just figured that out in another problem. So that's that C sub D, okay? Then the second thing is it compares the Reynolds number for the model and a prototype whose velocity is 60 miles per hour. So basically, what you're looking for is, what is this ratio? So what does it mean when it says pressure will affect the viscosity but does affect the density? So we can drop mu. No, rho is a function of density. So our density is a function of pressure. So if you take a look, it says it's pressurized, and that's why the air density is 3.33. If you go and look at it in standard conditions, yeah, not rho, then the rho is going to change. Okay? And now all we have to do is figure out what the drag force is. And just as a hint, you should get, if you do it correctly, that those are equal to each other. So you can just figure if they're equal to each other, then the drag forces are equal to each other. So how do you find the new rho? You look it up in the back of the book. And it's a pretty standard one. You may even have it memorized, like that 62.4. So the only thing here you have to be careful of is that length scale, which you're going to find in the Reynolds number. Okay, so what I'm going to do is I'm going to go on to 7, and then I'll come back and answer any questions that people might have about the, let's go here, question 3. I don't think I can do much with this, but we'll try and make it a little bigger. Yeah, there's a good chance. What is the scale for? Hold on. Actually, the drag forces are not, the Reynolds number is equal. The drag coefficient might be, but the drag forces are never equal. Oops. All right, so let's take a look here. Let's see if I can do something. Yeah, look at that. All right. Oh, we did do number 5. Great. All right. So here we go with non-dimensionalization. And this is something that actually looks worse than it is, because anytime you have stars and stuff like that, it's a pain. So note the term on the right-hand side that is right here. This is, I may have just lost my pen again. So this right here, there it is. That's the kinematic viscosity. All right. So the first thing you have to do is non-dimensionalize each one of the variables. So we're going to start with u. Now let's start with x. So what we want to do is we want to find an x star. And the way we do that is divide it by a characteristic length. And so every single one of those, so if you have a u star, it's going to be our u divided by v sub 0. What's our v star going to be equal to? Yeah, we did it right before break, which of course means, yeah. So this is going to be equal to v divided by the same characteristic velocity. And in fact, here, we might as well put this up. If we have our y star, what's that going to be equal to? Yeah, y divided by L. So let's look at the ones that might be a little bit, okay, did I make this big enough or not? So our P star is going to be equal to our P, and it tells you right away, divided by rho V naught squared. So what do we have left here? Okay, so characteristic quantity is when you're given a problem, there is usually a velocity and there is a length, and that's what you use to divide this by. And this is sort of a simplified version of if you got into graduate fluids, but basically there is some velocity that says that is part of the problem, and you use that. And there is some length that is part of the problem, and you use that. And it's for every velocity and for every length. Does that make it a little easier? Okay. All right. So if you look at this, we have everything here. Is there anything that we're missing? No. So let's do some of this. The easiest way to do this is, for example, when we want to replace, and I'll start with u, u is actually equal to u star v naught. So, and our x is equal to x star L. So our du dx is equal to du star v naught divided by dx star times L. So how would we make this dimensionless, which means you have to have a star in it, in the particular quantity? What should this look like? Yeah, so this is equal to V naught over L du star dx star. And that's what you're going to do for every one of them. Let's try another one. So we have u du dx, which we already know. So u is u star times v naught over L du star dx star. So where did I get this? I got it from this. So this u du dx is just equal to v naught squared over L u star du star dx star. Okay, so why do we do this? All right, and you'll see it from this. If you remember, when we non-dimensionalized everything, we ended up with some terms that had a dimensionless parameter. okay? And what that means is, and this is going to be one of them, you're going to have as one of your dimensionless parameters, actually your only one over the Reynolds number. So what happens is when you look at your situation and you see that you have a very large Reynolds number, what that means is that particular term is the most important term, and every other term can be considered negligible. And so what that says is that now, instead of saying, well, this doesn't count and this doesn't count for whatever reason, you know that for this particular flow, that only one term is going to be important. And what I can show you is, and you're going to have to do all the work anyway, so what you're going to end up with is this. Once you do all of the work, which you will, this is going to be minus dp star dx star plus, this is the kinematic viscosity divided by this, d squared u star dy squared star. Okay, what? Was that a question or a comment or a understanding or? Okay, so how do we apply the Reynolds number? Oh, an aha moment. Oh, good, that's even better. Is that, yeah, that's a star, you know my writing. So how did we get that? Well, basically what you're going to do is use this. So it's going to be the exact same thing. So P is going to be equal to P star rho V naught squared, and then you're going to put it into this like we've done with the rest of them. Minus 1 over rho, and then you're going to replace the P with P star rho naught squared, and you're going to replace the X with X star times L. So again, if we take a look at this, what is this right here? Not the Reynolds number, but close. No, the entire one. That entire expression, 1 over the Reynolds number, exactly. So this is 1 over the Reynolds number. And so what that means is if the Reynolds number is low, then this term right here is, is important. Yeah, that funky V is the kinematic viscosity. Just think of it looks kind of like a seagull or something. So then that term is really important and the rest of them drop out. If instead that term is not important, then that term drops out. Why did we? Oh, so what does show up with the rho? What happened to the rho? That's a good question. What is the kinematic viscosity equal to? I'll tell you, mu over rho. So we got rid of, if you look here, all right, it became part of this. Because again, remember we've got that part from this. Actually, I take it back. What happened to it? It canceled out with this. Where did the first equation go? What do we do with it? Which first equation? Oh, this? I figured you'd have no problems with that one. I took the second one because it was really easy. All right, but here, what if the Reynolds? Well, when you non-dimensionalize, you'll see what happens to it. And we will call it good. Okay? That's an easy one. It is not mysterious. I actually did it in class. So, all right. So if the Reynolds number is large, that's exactly right. So if this Reynolds number here is large, then 1 over the Reynolds number is small, and that means that this last term is negligible, and we can get rid of it. And that's why you do this. It's not just to torture you guys. What do you mean you disagree? How do we know if it's large? Well, you calculate it. So that's what I mean. Oh, yeah. That's what I mean about, then you apply this to a particular situation and you calculate it. And frankly, it's not just, whoa. Let me explain something and then we'll come back to you guys bothering me. What happens is when you get to equations like this, then you're going to have to do some kind of computational fluid dynamics to calculate what these are. But is this in comments that we calculate each and every? So here we actually only have one-dimensional group. And if you remember in class, we had one as well, where we have, remember, 1 over the Froude number minus squared. So there aren't going to be very many. And so is this in wetting materials? What part is the Reynolds? So this is the Reynolds number, but it's actually 1 over the Reynolds number right here. So you generally expect 1 or maybe 2. It depends on, again, what the problem is like, whether you have like a free surface, so we have the Froude number, whether you have viscous forces, so we have the Reynolds number, etc. But I'm not going to do something, yes, we did do number 5. I'm not going to do something really, really difficult. I mean, this is as bad as it would get, okay? Oh, I thought I'd set you up for the recording. How was my break? It was great. Are you asking everybody? Actually, my break was terrible, but that's okay. Oh, okay. You get to hear all about it in class. So the last thing I'm going to say, and then I'm going to go home because I'm starving. Let's see who's left here. What do we have? So the 61 of you who are still here, no, you can't wait. I'll talk tomorrow. So why doesn't everybody go and eat something? Yeah, you're starving. Gonzaga is probably gone. And oh, you are. Are you watching the game? What is it? You must have it on Sunday. Okay, go watch it right now. All right. And I will see everybody tomorrow.